Is this working? Yeah, good. Okay, so this is a mathematical mystery. Okay, so in the reinforcement learning community, planning when you have a long time horizon is considered to be a very hard problem, right? So if you go and you look at, there's lots of evidence for this. Part of it is just where the research is. But part of it is also just where you see applications. So if you go and you look at reinforcement learning in the real world, it's almost all Horizon 1, otherwise known as contextual bandits, right? There's a lot of literature where people are trying to do hierarchical reinforcement learning or reward shaping or some sort of regularization towards a shorter horizon. Each of these is trying to address a problem where the long-term planning is hard. Okay, so that's interesting. So if you go and you look at what's going on in reinforcement learning, clearly long-term planning is hard. Now, the weird thing is that if you go and you look at PAC-MDP results, theoretical reinforcement learning algorithms, there's no real dependence, no essential dependence on the horizon. That's kind of odd. So there's an extreme disparity between the theoretical results we have and what we observe in practice. Okay, so in a typical episodic reinforcement learning setting, you're thinking about a situation where you have a sequence of time steps. The learner is going to sample a trajectory. The trajectory is state, action, reward, over and over again until you get to the end of the horizon. Your goal is to find a policy that maximizes the sum of the rewards observed in expectation. And then the question is, how many rounds does it take to find an epsilon optimal policy? Or maybe you want to think about a regret version of this, where you add up the regrets over the process of doing the exploration. All right, so there are actually tight upper bounds now. So if you go and you look at these bounds, there are often dependencies on the horizon, big H, but these tend to be, these are all superficial. So for example, maybe you imagine that the reward at each time step is bounded by 1, and the sum of rewards is bounded by H. And so you get kind of a superficial dependence on H just because the range of the rewards is dependent upon H. Or maybe you're counting the number of steps, but it's really the episodes which are the independent objects, and so you should really think about the episodes, right? Or maybe there's non-stationary dynamics that are kind of equivalent to a stationary state space, which is H times larger. So these are the reasons why H appear in these upper bounds. All right, so they're essentially matching lower bounds, but they use a contextual bandit or bandit-style construction. Right, so I guess the question is the hardest RL problem a bandit? Because that's kind of what the math says right now. Okay, so the open problem is around trying to resolve this. And you might say, oh, this is just the story's finished, based upon what I just told you here. In fact, the hardest problem for reinforcement learning is a bandit problem. And then, we're done. We've solved bandits pretty well. But maybe that's not true. So the question is, can you prove a lower bound that depends upon the horizon in a pretty non-trivial way? So how do you imagine getting at this? And in order to get at this, because the upper bounds and lower bounds match, you have to think about changes to the setting. So what kind of changes to the setting would actually be useful? One of them is commonly you assume that the rewards are bounded from 0 to 1 or equivalently 0 to 1 over H, and then the total sum of rewards is bounded 0 to 1. Maybe this is not the right assumption. Maybe it's actually the case that the reward is delayed and sparse, and that's what makes it hard. So you want to think about a situation where there's no intermediate rewards, there's only kind of a success or failure at the end, so that the sum of the rewards is equal to the largest individual reward. So that would be this kind of assumption. maybe it's possible to prove something which matches these empirical and algorithmic intuitions using this kind of assumption. Another possibility is has to do with something which is non-asymptotic, basically. So if you look at these results, they're using an epsilon which is quite small, 0 to 1 over h. Maybe it's the case that when epsilon is larger, there's some non-trivial dependence upon the horizon required. Okay. Another common assumption is that you're working with tabular reinforcement learning, right? So you have individual states, you're learning some sort of policy which just conditioned on the state chooses what to do. Maybe instead we should be thinking about function approximation. And maybe somehow introducing function approximation or competing with a policy set introduces a dependence upon the time horizon, right? So there's now work addressing the function approximation setting directly, but we don't have a lower bound yet, which really exercises the upper bound that we have. Okay, so this is the essential problem. The PAC-MDP results kind of very much contradict the practical intuitions. How do we actually find some sort of H dependence in a lower bound? Under what assumptions would you actually create an H dependence, which is essential, not something which is superficial? And what does that look like? Right, and maybe that's a better model for reinforcement learning than what people are using right now. Are there any questions about this?
Maybe one short question or solution.
Yeah, it'd be great to have a solution. So unfortunately, so that's a good question. The reason why it's a good question is because I have a small bit of business to do before we move on to Alekh. But no money here, as far as I know. Okay, so the small bit of business that I have is Seb cracked an open problem from last year, and there was some money on that. So I'm paying up right here. Thank you. First order contextual bandits.
You should give a check so you can post